Chapter 4, slides 1 through 18. Okay, so far, chapters 1, 2, and 3, we've done quite a bit. We've tried to elevate your understanding of how organic molecules are represented, getting you comfortable with bond line structures, right? Those assumed hydrogens, the ends and bends of a carbon structure, assuming lone pairs on heteroatoms. So we've gotten you comfortable there. We've also reminded you of electronegativity and the effect of dipoles, what that effect has on physical properties like boiling points and melting points. And then we reminded you of some basic acid-base chemistry using small molecules that you were pretty familiar with, right? HCl and water, introducing you to electron pushing. We also have discussed what makes certain instances more stable, and we've bringing induction into that, bringing orbitals into it, and bringing a whole new concept called resonance into it. For the next two chapters, we're not going to be doing any chemistry. So chapter 4 and chapter 5 are solely dedicated to representing those carbon molecules. So we're going to take our bond line structures, and we're going to first learn in this chapter how to name them, and then using what we understand now for geometry and hybridization, how these molecules as a whole behave three-dimensionally, like how they, what effects they have as three-dimensional molecules. We're going to try to understand them outside of being stagnant-looking structures or drawings. So we're really, chapter 4 and chapter 5, there's no chemistry happening in these chapters. It's really learning to interpret a more, a higher level of understanding of these three-dimensional molecules. Okay, so let's begin. Slides 1 through 18 talk about nomenclature. This is just a fancy word for naming. We're going to be focused on simple alkanes. What is that? Well, alkanes are hydrocarbons. These are compounds that only have hydrogen and carbon in them. Alkanes can be part of a larger molecule. There might be areas that are very alkane-like, but specifically hydrocarbons. So we're talking about saturated hydrocarbons, and saturated hydrocarbons are compounds that do not have pi bonds or rings. This means that if I had 3 carbons, say propane, 1, 2, 3, as long as that 3-carbon system doesn't have any rings or pi bonds, I know that it will have the maximum number of hydrogens around it. So for a C3 molecule, the saturation of a C3 carbon molecule is going to be, let me count the hydrogens around it that are assumed to be there, 1, 2, 3, 4, 5, 6, 7, 8. H8. That is a saturated hydrocarbon. Try it yourself. If you were talking about propene, that's still a C3 molecule. How many H's would be surrounding these 3? If you count them out, you'd come up with 6. We know that saturated hydrocarbons have 8. So anytime you add more pi bonds or a ring, the number of hydrogens around the carbons diminishes. So we're going to be learning to name organic molecules, and we're going to start simply, and we're just going to focus in on alkanes or saturated hydrocarbons. So when we're communicating about molecules, each molecule, if it's unique, if it's different from another molecule, the list of rules that we've come up with should come up with a unique name for it. So for the isomers that you guys were trying to figure out in the previous chapters, are those, if you were given 2 molecules and you were wondering, are these 2 molecules the same? Because as you know, we can twist single bonds and make them look different, even though they might be the same molecule. Well, here's something really nice about chapter 4. if you can't get your head around looking at two molecules and figuring out if they're just twisted conformations of the same molecule, try naming them. If they truly are different molecules, you will come up with a different name for it using the set of rules that chemists have derived. So we're going to use these, I'm going to teach you how to use these sets of rules to name very simple alkane structures. What do you notice about the above hydrocarbons? They all have the same ending, ane, because they're all saturated hydrocarbons. No pi bonds, no rings, but what differs is the number of carbons. First one has 3 carbons, the next one has 4 carbons, and the last one, 1, 2, 3, 4, 5, has 5 carbons. So you'll notice that their prefix changes based on the number of carbons in the chain. So let's take a look at this. Back in 1892, as the number of organic molecules started to grow, they needed to have a systematic system of way of identifying different molecules, and everyone needed to use the same system. So it was born the IUPACS system, or the International Union of Pure and Applied Chemistry system, right? It's kind of a mouthful. So the IUPACS system is how we say it. The first rule of the IUPACS system is to find the longest parent chain. So you might have a molecule that looks like this. And what you can do is take your pen or a highlighter or something and try to trace without picking up your pen the longest chain of carbons. 1, 2, 3, 4, 5, 6. Ooh, 6. Can I beat 6? I don't know. Let's try another one. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, I just did 8. Great. Anything better? 1, 2, 3, 4, 5, 6, 7. No, it doesn't beat 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, that looks good. How about 1, 2, 3, 4, 5, 6, 7, 8. Nope, can't do that. No, 9 seems to be the best. And that's exactly what we see here. Right? We see 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the path that I drew over to the right. Okay, found it. Step 1, check. We have found the longest parent chain. What next? Now we have to name that chain, and we have to use a suffix for the longest chain. So I'm only going to hold you responsible for 10 and let you know that I think the first 4 are the only ones that are not really that intuitive. So if you have 1 carbon, and that's your longest parent chain, I don't know, something like CH4, that's the prefix meth. Methane gas. Think about it. Methane gas is a gas because it's just got 1 carbon, there's no hydrogen bonding interactions, there's no dipole, and it has very little surface area for van der Waals or London dispersion forces. So CH4 is a gas at room temperature 1 atmosphere. That's your methane gas. Think about your farm. If you have 2 carbons as your longest chain, think about spirits or your beer, ethanol. That is eth. If you have 3 carbons as your longest chain, think about barbecuing, propane, right? That's just a 3 carbon, and again, it's a gas. What's holding it together? What's holding one propane molecule to another propane molecule? Well, no hydrogen bonding, no real dipole to speak of, a little bit more surface area than methane, so we pressurize it and have it in a propane tank. How about 4? 4 prefix is your bute, for butane, like a butane cigarette lighter. It's only barely a liquid at room temperature in 1 atmosphere. You shake that little lighter and you hear if there's still liquid in there, right? It's barely a liquid at room temperature in 1 atmosphere. All right, so once you know those prefixes to use, the 5 through 10 are pretty straightforward because you guys probably all took geometry and know pent for 5, hex for 6, hept for 7, oct for 8, like your octane rating. 1, 2, 3, 4, 5, 6, 7, 8. There's octane for your gasoline. 9, known and 10 dec. We do have ones for 11 and 12 and onward, but I'm only holding you responsible for 1 through 10. Okay, so once we've found the parent chain, we're going to name it. Let's look at this example here. We've got in red the longest parent chain. 1, 2, 3, 4, 5, 6, 7. So what's the parent name for this molecule, given what we just learned about prefixes? If you said heptane, you would be correct. So we've just named our parent chain, heptane. Okay, here's the problem though. In this molecule, there are 2 different ways to arrive at 7. And I've traced, these are both the same molecule, but I've traced the 7 parent chain differently. They're both 7, but the things that are dangling, the substituents that are dangling off of the parent chain, have different patterns if you look at it, depending upon which pattern you chose, which parent chain you traced. If you look on the left, there are 3 substituents off of your parent chain. But if you'd chosen to trace a different parent chain that still arrives at 7, you only see 2. And you might think, oh, isn't it easier to just name 2 things than 3? But as you'll find, there are some complex patterns that might arise when you have fewer substituents. So the one that I'm pointing to, the substituent that I'm pointing to here, is much harder to name than the more simplified, smaller substituents. So the rule of thumb is, if there are a couple different ways to trace the same number of a parent chain, choose the one that has the most number of substituents hanging off. Ultimately, trust us, it will be easier to name. So this is the way we want the parent chain to be traced. And then there's 3 substituents off of it. Okay, let's talk about substituents. I've identified parent chain. I know which parent chain in a tie to pick. Now what I need to do is start numbering my parent chain and naming the things off of it. Let's start with this example. I've found the longest parent chain and I'm numbering it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's decane. Done. All right, now I gotta account for those substituents that are hanging off of decane. What are they? Well, I numbered the long parent chain, and now what I'm gonna do is I'm gonna use my prefixes, but I'm not gonna use the ending ane. Ane is reserved for the parent chain of hydrocarbons. The prefix -il is used for things that branch off of your parent chain, but we're going to use the same prefix system. Okay, so the suffix -il goes with the same prefix system. So let's start on our parent chain. The first substituent I hit is at carbon 4. So at 4 hyphen, there is a 1, 2, and I'm using these primes, 1 prime, 2 prime, because not to be confused with the regular carbon chain. This is a dangling chain of 2 carbons. So it is eth-il. Okay. At carbon 5, I hit another substituent. 1 prime, 2 prime, 3 prime. It's got 3 carbons in it. So at carbon 5 of the parent chain, I hit a 3 carbon or prop-il chain. At carbon 7 of the parent chain, I hit a 1 carbon, right? Ends and bends, a 1 carbon methyl. Okay, so now I've got all of them. What do I do next? Well, I'm going to alphabetize the substituents. I have an E for ethyl, I have a P for propyl, and I have an M for methyl. Unfortunately, we don't put them in the order of their numbers. We put them in alphabetical order. So I'm going to write 4, ethyl. Next, 7-methyl. Next, 5-propyl-decane. That is the full name for this molecule. Now, I want you to notice a few things here, right? So we did alphabetical order, E, M, P. The parent chain always goes at the end. You also notice that I used hyphens. Whenever you're separating a number from a letter, you're going to use a hyphen. If you're separating a number from a number, you're going to use commas. And if you have a letter, and then you start another word, another letter, there's nothing in between. So if you look, propyl-decane just flows into the next word. We didn't use a hyphen or a comma or anything there. It just was 4-ethyl, 7-methyl, 5-propyl-decane. Let's get some practice because there's a little bit more that you need to know. And I think you'll learn these rules and skills as we do a few more examples together. Let's start with A. Find the longest parent chain. 1, 2, 3, 4, 5. Okay, number the longest parent chain. Do I go 1, 2, 3, 4, 5? Or do I number it 1, 2, 3 in the other direction? Well, take a look at the substituents off of the longest parent chain. If you order the numbers from left to right, you come across the first substituent at carbon 2. If I'd started numbering in the opposite direction, the first substituent I would hit would be carbon 3. So I want to choose numbering my parent chain so that the first substituent I get to has the lowest number. So I actually got lucky in numbering it from left to right in this instance. And I'll do everything as mapped, as shown. So the longest parent chain is pentane. I like to list all of the things and then I put them in order at the end. Don't try to write it all in a row right from the beginning. It's too hard because sometimes you just don't know how things are going to get spaced out. So since you're actually figuring out the name of the molecule from right to left, it's easier just to list all the components of the name and then put things together afterwards. Okay, so you'll see me write things vertically and then write it horizontally. So pentane. At carbon 2, there's a methyl group. At carbon 3, there's a methyl group. Now this is a good example because we don't want to say 2-methyl, 3-methyl pentane. It's kind of redundant. Whenever you have the same substituent but in different locations, even if you have it in the same location, all we're going to do is group them so that we don't have to write so much and add another prefix, in this case, di. So the name of this molecule is 2, 3, notice the comma, dimethyl pentane. At 2 and at 3, there is a methyl. There are 2 methyls, dimethyl. One's at 2, one's at 3. Let's try this again. Let's do example D, just to the right. Longest parent chain, doesn't matter which one I start with. 1, 2, 3, 4, 5. I could have started, doesn't really matter. 1, 2, 3, 4, 5. It doesn't matter which methyl I start with. So 1, 2, 3, 4, 5. It again is a pentane. Do I start numbering left or right to hit those substituents? There's 2 substituents. This is a good example because I get A lot of students who think that when I number 1, 2, 3, 4, 5, a lot of students will write 2-ethyl. But that is wrong. This is not a 2-ethyl substituent. There are 2 different CH3s off of carbon 2. It's not a 2-carbon chain. It's a carbon, stop, and another carbon, stop, right? Those are 2 different groups. That is a 2-methyl, 2-methyl. And since it's redundant, it's di. So how does this one look? The correct name for this one is 2, 2, dimethyl pentane. I'll let you do B, E, and C on your own. Now, sometimes you just can't avoid it, and you'll end up with a very complex substituent hanging off of your parent chain. And these can get a little tough. So I figured we'd do a few examples. We're going to use the same rules that we've used, but we're going to add parentheses. So let's start with the longest parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that the best I can do? 9. 1, 2, 3, 4, 5, 6, 7, 8. Yep, I think that's the best I can do. So 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Does it matter which way I start numbering? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No matter which way I start numbering, 5 is the first carbon I come to with an appendage off of it. Substituent. So longest parent chain is nonane. And there's a substituent off of it. Okay, I like to highlight. Every carbon should have some highlight to it, right? I've touched basically every carbon with my highlighter of some variety. Okay, so what we're going to do is we're going to focus now on this very complex substituent. It's comprised of 1, 2, 3, 4 carbons, but I can't write just butane, okay? The reason I can't write butane is that if you have, let's say you have this really long parent chain. If I have a 1, 2, 3, 4 carbon, 1 prime, 2 prime, 3 prime, 4 prime, this long straight chain appendage is butyl. It's a butyl group, okay? But this is not a long chain. The blue that I've highlighted is not a straight chain directly off. It's a branching chain, okay? So when you have appendages or substituents that are branching and they're not straight chains, you're in for it. You're like, okay, this is a complex appendage or a complex substituent. I gotta take my time here, okay? So you're almost gonna do another sort of mini naming project for that appendage. This one would be easy. The one below I have is pretty easy, right? If you have an appendage and it's just got like a 3 carbon chain off of it, 1, 2, 3, it's propyl, easy peasy, right? Ethyl, propyl, butyl, straight chain like I had in the other examples. In that first example, what you notice is I kept it very simple. I had just very normal straight chains. So it was ethyl, propyl, methyl. Once you get to propyl, things can start branching. Pentyl, if it just says pentyl, it's a straight chain of 5 carbons. So how do we name these? Let's get some space here. What we're going to do is we're going to treat it as its own little project. Starting from the carbon directly attached to carbon 5, I'm going to start numbering the longest parent chain of the substituent. So, but I always start at the first carbon off of my parent chain. So you don't have to worry about which number, like, where do we start numbering? Well, that one's at least easy. You start at the carbon right off of your parent chain. So we're going to call that 1'. Now I want to name the longest chain starting at 1'. If I went left, I would only have a 2 carbon chain. But if I go right, I'll have a 3 carbon chain. So 2', 3'. Okay, so I have a 1', 2', 3' substituent. But off of that propyl, right? Because I'm going to name that longest substituent chain. And I still use the -il. I still use the ending YL. I have a propyl group. But at 1, I have a carbon. I have a methyl. Okay? So that substituent is called, right? We start, where is the substituent? The substituent is at 5, hyphen. And in parentheses, because it's its own sort of naming game, we're going to say it's a 1-methyl propyl substituent. And that 1-methyl propyl is at carbon 5 of the parent chain. So putting it all together, I have 5 1-methyl propyl nonane. This is the final answer for this compound. Let's do another one because these can be hard. You'll get the hang of it though. Longest parent chain, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8. No. 1, 2, 3, 4, 5, 6, 7, 8. No, 9 is the longest. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks very similar to the last one. Doesn't matter where I number because the first thing I hit is at carbon 5, and no matter which direction I started numbering, 5 is the first substituent. So let me highlight my substituent. Here is the substituent. This is a complex branching substituent, so I'm going to number the first atom off of the parent chain as 1', and now I'm going to find the longest chain, 2', and it doesn't matter if I go up or down. I'll go down, 3', doesn't matter. The longest parent chain off as a substituent is 3. So it is, again, propyl. So my longest chain, 6, 7, 8, 9, is nonane. I've named it. Hold on to that. So I've got a propyl appendage, but I also have a group at 1. So I have a 1-methyl. And I have a 2-methyl. Okay, let's put that whole thing together. So I have an appendage at 5 that, in parentheses, is a, oh, look, methyl. There's 2 of them. So I have a 1, 2 dimethyl propyl, close parentheses. That is the name of the appendage. At 5, there's a 1, 2 dimethyl propyl. Put it all together. 5, 1, 2 dimethyl propyl nonane. That is a long name. You'll get the hang of it though. What about rings? So we've talked about chains, and now we want to look at some ring systems. What we do here is we add the prefix cyclo. So if your longest chain actually has a ring, then you're going to use the cyclo prefix. So in this case, we have cyclopropane, 1, 2, 3 carbons. We have cyclobutane, 1, 2, 3, 4, and cyclopentane, 1, 2, 3, 4, 5. Might be a little difficult figuring out, where to start numbering. It really doesn't matter unless you have an appendage. Then you can start numbering your cycloalkane on the carbon bearing the appendage, since you have a choice of where to begin, because there is no end, right, to the ring. So let's do an example, and this will help us in understanding a few more rules. Okay, let's look at the first one. We have longest parent chain is cyclo. So we have a cyclo, and how many carbons is it? 1, 2, 3, 4, 5. I was just counting. I don't know what my numbering system is going to be yet, but there are 5 carbons. So this is cyclopentane. Okay, so I got to figure out where to start numbering. And if you'll notice, I have 2 appendages off of my cyclopentane. I have a methyl and an ethyl, right? Here's a 1' and a 1', 2'. So I have an ethyl group and I have a methyl group. I'm probably going to want to start with an alphabetically. So E comes before M. So I'm going to number my parent chain 1 at the ethyl, so that I have a 1 ethyl. That's the lowest number I can get, and I should put it first. Now, when you number around a ring, you have a choice. Do I number clockwise or counterclockwise? Well, I want to hit the next substituent as soon as possible, so I'm going to number the methyl at 2, 3, 4, and 5. So this would be the correct numbering order for the cyclopentane. So I have a 2 methyl. And these are 2 different groups, so I can't combine them with a di. So if I put them in alphabetical order, this molecule would be 1 ethyl. The 1 is often, sometimes people leave a number out. If you ever see an appendage without a number in front of it, it's assumed to be a 1. I like to put them in. I just don't want to assume. There's so many assumptions in organic chemistry. I like the 1 being there, but I will warn you, sometimes you will see, if you just see the start of a name as ethyl propane, you're going to assume, and that doesn't make any sense, but if it's at the first carbon, then it is going to be it's going to be 1 in front of it. It's an assumed 1, but I'm going to write the 1 in. 1 ethyl, 2 methyl, cyclopentane. And there you go. What happens when the longest chain is not the ring? So here's an example where you've got to choose between cyclobutane. Okay, you can't do this. Okay, this is a no-no. You can't say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's no name. You can't do that. I know I said without picking up your pen, longest chain, but it has to be a chain or a ring. So you're either going to choose to have the parent be cyclobutane, that's a 4-carbon chain, or 1, 2, 3, 4, 5, pentane, 5-carbon chain. Longest parent chain wins. So even though there's a ring here, I need to number it starting closest to the substituent. I name my parent chain. This is pentane. And what I'm showing here is that in this case, the ring is a substituent to the longest parent chain. So I see that at 1, there's a cyclobutyl. So this is 1 cyclobutyl pentane. Or Some people just might write cyclobutylpentane, and the 1 is assumed, but I'm going to write it as 1-cyclobutylpentane. Final answer. How about you try the last one? Sometimes that when you have appendages, you're going to see a three-dimensional difference between dangling appendages. And we're going to talk a lot more about this in chapter 5, but I'm going to introduce this concept here. So if you have an example, 1, 2, 3. So this is cyclopropane, and there's a 1-methyl, and there's a 2-methyl. And when you put this together, it is 1,2 dimethyl cyclopropane. And what you're going to notice is that sometimes, especially in ring systems, you'll see wedges and hashes used. And what we're going to learn in chapter 5 is that the two molecules written below, if I just change the straight bonds to be more specific about the through space connectivity here, this is similar to having double bonds being in a cis or trans conformation. These are two different molecules. The one on the left we'll call A has both of the methyls coming out at you or up. And you can see this in a three-dimensional model. Compound B has 1 methyl up and 1 methyl down. So what this means at each of these carbons, if you draw the assumed hydrogens at those carbons, for compound A, if both methyls are up, then the assumed hydrogens must be back. Because those carbons are sp3 hybridized, they're tetrahedral. So if the two bonds of the ring are in the plane, the tetrahedral orientation of the wedge and the hash are present. So the hydrogen must be hashed. In compound B, for those same two carbons, the hydrogen on one has to be forward, coming out at you, and the other one has to be back. And you can see this in the models. If the two substituents are on the same side, both up or both back, this is a cis configuration. So you would have cis and then the name of the molecule, which we just named above. So this would be cis 1,2-dimethylcyclopropane. For B, you would see that the relationship between the methyls, one's up, one's back, one's up, one's down, one's forward, one's back. This is a trans or opposite relationship. We're going to look at this a lot more in chapter 5, but I just want you to be aware that you can have this difference of isomers for a compound by the orientation of substituents. So to summarize, you're going to identify the parent chain, right? The longest consecutive carbon chain. Now I want you to understand, like, if you have a really long chain and there's an oxygen all of a sudden, like, that is a break of the chain. That is not, you can't go through the oxygen to name the longest parent chain. You can't do that, right? It has to be all carbons, hydrocarbons. Okay. Then once you've identified the name, you name it with its correct prefix. You number your parent chain, assigning your location to the substituents with the lowest number. And then you name your substituents where they're located on the parent chain. And then you list those numbered substituents on the parent chain in alphabetical order. Okay. And here's one of those things that I want you to understand, that when you're putting things into alphabetical order, let's say you had a bunch of substituents off of your parent chain. You had let's say one methyl or one propyl, and 2-ethyl, and 3-propyl. Okay, so let's say those were the substituents off of some crazy parent chain, okay? You would say, oh, well, the propyls go together, right? Those are redundant, so we're going to give it a di. So it's going to be 1,3-dipropyl, right? And then you put it in alphabetical order, and D comes before E. Wrong, okay? Actually, you're going to do alphabetical order before you assign the whole di thing. So the 2-ethyl is going to go first. So it's E comes before P. So the correct order is 2-ethyl, then 1,3-dipropyl. It's the actual substituent that you alphabetize, not the fact that you have dipropyl. If you had 3 propyls, it would be 1, 3, whatever the number is, 5-tripropyl, right? If you had 4 substituents, it would be tetra. But I just want you to be aware that you alphabetize the actual substituent. You don't use the di, tri, tetra, like prefix of the prefix, essentially, to alphabetize. I leave you with these pretty challenging problems. If you further look into the textbook, this one is, if you read the text for how to name bicyclosystems. For this course, I will not require it. I usually have majors learn to do bicyclosystems, but I'm not going to require you guys to learn bicyclosystems. But if you want an extra challenge, you can read up in the text on how to name a bicyclosystem and try this one as practice. The rest of these you should be able to do. Okay, so I'm only going to complicate matters only with one functional group, and that is if we have a halogen off of our chain. So I'm going to make our alkanes a little bit more interesting and put some functional group on them. If you have a bromine on your chain, it's going to have the prefix bromo. If you have a fluorine, it's fluoro. If you have a chlorine, it's chloro. And if you have an iodine, it's iodo. So if we were to name the following molecules, all we're going to do as we get to new functional groups is we're just going to tack on an extra rule as it pertains to that functional group. So this will be the first and last functional group we do for a while. First one, find longest parent chain. 1, 2, 3, 4. Okay, 4 is the longest carbon chain. It's butane. And I'm going to start numbering on the right because I'll hit the bromine faster that way. So I see that I have a 2-bromo. So this is 2-bromobutane. If I had 2 bromines off of carbon 2, I would have another 2-bromo, and I could combine them, and that would be 2,2-dibromobutane. But I'll leave that out for now. This would be called 2-fluoropropane. Longest parent chain, I hit the fluorine at 2. What about this one? Longest parent chain, 1, 2, 3, 4, 5. It's pentane. There's a 1-chloro. And I chose to label the 1 at the chlorine. 1, 2, 3, 4, 5. And I see that I've got 2 substituents, right? The chlorine and the methyl group. I have a 4-methyl. I have to alphabetize. I've got chloro and methyl, so it's 1-chloro, 4-methyl, pentane. Last one. 1, 2, 3, 4, 5, 6. This one is 1-iodo-cyclohexane. Okay. You guys can practice naming with the ones I've given you. You can go to your textbook and get some more practice, and I'm sure there's some on homework as well. Now we're going to do a little bit of terminology. You could use this bottom example to try and name that one too for more practice. But I want to talk a little bit about some terminology words that we're going to use a lot in this course. So the first retrieval cue is when a carbon has substituents attached to it. We can actually start using words like primary, secondary, tertiary, and quaternary. These are going to help us understand how bulky the molecule is at a given position. So if you think about methyls, ethyls, butyls, all of these things, and you think about inductive effects, way back to chapter 1, when I was trying to get you to tell me if something was donating or withdrawing. Is that a donating group or an electron withdrawing group? What you'll remember is that methyls, ethyls, butyls, just hydrocarbons in general, due to their small dipole, but due to the fact that they're these balls, these tetrahedral balls of electron cloud density, they act as donating groups, and they're tetrahedral. They're kind of bulky. So when you have a carbon that is primary, like the ones that I'm indicating, all of the purple primary carbons that I'm showing you, the ones on the ends, are primary. Why? Because they're the ones that only have one carbon attached to them. A carbon with only one other carbon bond, and the rest of it's just filled with hydrogens. These are all called primary carbons. Secondary carbons are the ones that have two carbons attached to them. So in green, I'm going to color code all of the secondary carbons. These carbons have, look at them, they have two carbons, and then they have two hydrogens that are assumed. So I'm highlighting all of the secondary carbons. Then we have tertiary. Tertiary carbons are the ones that have three carbons off of them. I only see this one. This carbon right here is tertiary. It has three carbon bonds. That means there's one hydrogen, right? There's one hydrogen assumed. And then there's this carbon that's tertiary. It's one hydrogen assumed, and that's it. And lastly, we have quaternary. Quaternary is where the carbon is flanked by all carbons and does not have any hydrogens at all. And you can see there's one quaternary carbon on this molecule. We're going to talk about primary, secondary, and tertiary the most. You can go back to your other molecules that you had for practice and see if you can color code them or label them as primary, secondary, and tertiary, or quaternary. We can extend this terminology to other functionality. So for instance, you have an amine. If the amine is just flanked by hydrogens, which it's a very specific molecule, then it's NH3, and that is called ammonia. Once you start putting carbon groups one at a time around that nitrogen, replacing the hydrogens, so if you have only one carbon attached to the amine, it's a primary amine. If you have two carbons attached to the amine, it's a secondary, and three carbons, no hydrogens whatsoever, it's a tertiary amine. Here's an example of two other functional groups. Here we have an alcohol. I'm going to go to the one way at the end. Here's an alcohol group. Okay. We define an alcohol based on what type of carbon it's attached to. So if the alcohol is on a carbon that's flanked by all carbons, it is called a tertiary alcohol. So notice you can never have a quaternary alcohol. That's impossible. That's why, as I mentioned, we're only going to be talking mostly about primary, secondary, and tertiary as it pertains to functional groups. Because the functional group of interest, we define that functional group based on the type of carbon it's on. The only time we don't do that is with amines. So the number of groups actually on the nitrogen, actually carbon groups on the nitrogen, is what defines the amine, like we did up at the top. However, groups like chlorine and alcohol, right, those are defined based on the carbon it's attached to. If the carbon it's attached to has 3 carbons off of it, it's a tertiary alkyl chloride. If the alcohol is on a carbon with 3 R groups or carbon groups around it, it's a tertiary alcohol. So it's slightly different in that terminology. You'll get used to it as we go along. But here's some practice, right? So provide the systematic name for the following compounds, and then you can also go back and indicate whether the halogen is primary, secondary, or tertiary. Say, for example, this bromine, I'll do the primary, secondary, and tertiary with you. This bromine is on a carbon that only has 1 carbon bond. The other are hydrogens, right? So the carbon only has 1 other carbon bond to it. So this is a primary bromide. You guys can try the rest. Other naming methods. Okay, well, we've just gone over the basic principles of the IUPAC naming system. These are the rules that were come up with by a group of people trying to systematically name molecules. There are lots of different other ways to name molecules. As a chemist, I get asked all the time by friends and family, why don't you know the name of, Nexium? What's the molecule look like? I'm like, I don't know. That's a trade name. Okay. Mevacor, right? What's that? What does that look like? Can't you tell by the name? No. If you gave me the IUPAC name, I'm sure I could derive it. A picture's worth 1,000 words. And so as you can see, the IUPAC naming system, it does fall apart a little bit as we go on because the molecules get so big that it's too onerous a task to be asked to try and name it. So drawing the molecule is so much better. And in the field, people have adopted generic names or trade names for different pharmaceuticals or even materials. They'll have certain names that really do not relate to the IUPAC system. So you can see here the generic name for this molecule is morphine, which we know is a painkiller, and it's named after the Greek god of dreams, Morpheus. So sometimes these names have history to them. One of my favorite trade names is Viagra, which as we know what this blue pill does, and this one was named by the employees at Pfizer, jokingly saying, oh, if we combine the words vigor and Niagara Falls together, we get Viagra. And so that's where the trade name came from. But obviously we can't derive the structure from the trade name. And as you can see in the upper right here, this is the IUPAC name for that molecule. Oh my God. There's a lot to learn on IUPAC naming system. They really truly did think of everything, but it's really hard to derive some of these names or let alone be given the name and try to draw the structure. So we're going to keep it pretty basic and simple. I'll give you some practice to look at, this is about as complex as they're going to get, or these other practice ones. I think this is as hard as it will get for you for naming. And we'll add a few rules here and there, but for the most part, drawing a molecule is so important to learn.